Hello, welcome to the talk. I'm Zhongyan Zhao, a research professor from Rice University in the United States. In this talk, I will present a new architecture for joint task offloading and routing in wireless multi-hop networks using biased backpressure algorithm. This is a joint work with Jackie Parazon, Gonjan Verma, Kevin Chen, Ananthan Swamy, and Santiago Segura. There are two types of task offloading. The first is one-time on-demand offloading that's usually seen in pathfinding, scientific computing, and data analysis. The other type, which is also what we work on, is recurrent task offloading that's usually seen in video surveillance, autonomous robots, or environmental monitoring, where each task contains a stream of jobs that each of these jobs are similar, like processing a video frame. Our setting is in a wireless multi-hop network in which there are three types of nodes: the clients, a dedicated relay, and the servers. And the network can be abstracted as a connectivity graph on the right-hand side. So each client can initiate multiple types of tasks. Right? What we know about these tasks are the job arrival rate of each type of task for each client, which could be different. And we also know the service rate of each server for each type of task, and the link rate of these wireless links. Offloading and routing are two types of decisions. There's where and how to get there. Imagine you have a car and you are in a big city, want to find a gas station. Sounds easy. Why don't we just find the nearest one? Right? But you might find these unhappy situations. Okay, so you have congestions on the road. So our goal is not only reduce the travel distance, but also avoid the congestions on the road or at the destination. So a better strategy is to check the state of the network before we go. This is clearly better, but you could still have the problem that after you set off on a road, the congestion condition changes and then you're stuck in the road. So a better strategy is to predict the future network state based on the current state and then make decisions. Of course, one could also say that we can have a centralized authority that collect all the information of all the cars and gas stations in the city and then make decisions for everyone. Right? And this sounds good, but in reality, this approach doesn't scale well, especially for large cities. So now let's look at the offloading cases. Here, centralized solution is actually quite common. It's often formulated as mixed integer programming, where a centralized scheduler will first collect the full network state, then compute the solutions offline, make decisions simultaneously for all the tasks. But because of the integer constraint on the decision variables, this problem is often NP-hard, meaning that its computational complexity scales exponentially with the size of the problem. Luckily, we can relax this formulation to a linear programming for our recurrent tasks. By considering task as a divisible liquid flow, so we can assign fractional rates as a probabilistic scheme for each task. So now this linear programming can be solved quickly. Right? So for example, we have this formulation here. We're going to minimize the total cost, such as latency or make span, by optimizing the flow rate assignment. So here, the cost of each task is linear. And then we have these constraints, such as the flow rate conservation, the inflow must equal to the outflow rate, and the server capacity and link capacity must be respected, so that they cannot exceed those capacities. Of course, the cost should be non-negative. So this formulation looks good, but actually it ignores the interference in wireless networks. For this link capacity, we actually don't know exactly the link capacity constraint here because of the mutual interference among wireless links. So now let's look at the second strategy in a distributed way. Here we make decisions in the separate stages, and each client also make their own decision at any time, so they can make decisions asynchronously. They will first decide where to go and then find the path toward that destination. So here, to evaluate how good this type of strategy, we're going to define an ideal benchmark for this separate offloading and routing. We assume that each client knows the real-time server states instantaneously at no cost. Then we employ the state-of-the-art routing scheme for wireless multi-hop networks. Here, and the offloading and routing based on backpressure because it has the maximum queue stability. We need to mention this state-of-art shortest path bias backpressure. So it has the minimal latency, maximum queue stability, and it can mitigate many of the drawbacks of the original backpressure. It has three main characters. First, each node has a per destination queuing system. And then we need to compute one time for the shortest path bias across the network. Basically, all pair shortest paths between all the nodes pairs. And lastly, we have this backpressure operation as runs in a fully distributed manner. It contains both routing and scheduling decisions in a wireless network. So now we turn to our approach. We are based on the shortest path bias, or SPBP, as well. So what's new here? So here the key point of this approach is that we model computing as sending jobs to a virtual sink over virtual links. So here, for example, in this, we have two types of tasks, so two types of commodities. And then we define virtual sinks for each of this commodity, right, representing their ultimate destination. Now for each computing nodes, they have a virtual link connected to this virtual sink. And the bandwidth of this virtual link represents the processing power of this node for this type of task. So now we have an extended connectivity graph that has both physical and virtual links. So we need to specifically talk about how we model these virtual links. So here the job scheduling operation runs like follows. So whenever there's a free processor on the server, right, this processor will grab a job from one of these queues based on the maximum waiting time of these queues. And then we model this operation as two virtual links, and they are in conflict with each other, and their link rate represents the processing bandwidth, or how many jobs can be processed per time slot. Now with these conversion, with this modeling of this computing, we now can show the full picture of our joint solution. Right? So here we just run the shortest or SPBP on the extended connectivity graph, but the computing operates in a continuous time domain. And the physical link scheduling is not impacted by these virtual links because virtual links are not in conflict with any physical links. So only the routing decision will be influenced by the existence of these virtual links. So the rest of the operation in our approach is just standard SPBP. Now we turn to numerical results. So we test our approach and the baselines on random wireless multi-hop networks with hierarchical architecture. So there are 3 tiers. The core servers has the highest computing power indicated by the size of the nodes, and they are connected to each other at the core, and there are groups of edge servers. Within the group, they are connected to each other, and they are connected to their own core servers for that group. And the tier 3 are the clients, who mostly connect to edge servers, but also occasionally connect to core server. The job arrivals has a mixture of streaming and bursty process. Time horizon is 1,000 steps, and the computing capacity link rates are configured here as follows. So we first test our approach on a scenario with 2 types of tasks. Task 0 can be computed both locally or remotely. Task 1 can only be computed remotely, so they have to be offloaded to somewhere. And we present 3 metrics: the make span, the average make span of different types of tasks under different schemes, the delivery ratio, and the number of hops the jobs have been traveled. And we can see that the separate offloading that only considers the QSI, the queuing state information, have the worst performance, right? Because it often offload to remote servers, indicated by the number of hops. But now for the green ones, we consider both the QSI, the distance between servers and the clients, as well as the server capacity. Now this can lead to a significant improvement on performance, even though they still underperform our joint solution. So here, remember that these separate solutions, they have ideal information, instantaneous information of the servers. Next, we compare our joint solution with the joint linear programming relaxation. In order to evaluate this joint linear programming, we actually have to make the test case simpler. First, we have to reduce to a single task type, and also relatively scale up the communication bandwidth of all the links 8 times. And so we can see that the joint linear programming approach performs similarly as our approach at the lowest traffic load. However, as the traffic load increases, the joint linear programming approach deteriorates quickly, and up to the point of the traffic load of 1.8, we can no longer find a valid solution for the joint linear programming. So the curve stopped here. In comparison, our joint backpressure-based approach, also the separate backpressure approach, biased backpressure approach, they both perform well as the traffic load increases. So in conclusion, we presented a solution of joint offloading, routing, and scheduling. This includes both job and link scheduling. So this is a fully distributed asynchronous solution where each client don't need real-time server-side information, and the task can be initialized at any time. So this is essentially a offloading without destination and a routing without routes. And it has best performance, good scalability, and queuing stability. So in the future, we can further incorporate the context switching cost in job scheduling, incorporate more complex task pipeline, the priority system, and also compatibility with regular data traffic. So these are the references Thank you for your attention.